Okay, so hello. Hopefully, this is the last video. We shall see, because I know probably past the first video, you're tired of listening to me, and that's fine. But nevertheless, we carry on. Okay, so we've talked about the principle in terms of when we're really talking about natural numbers. We talked about principle of mathematical induction, principle of complete induction, PCI, and now we're going to talk about a third property to sort of characterize the set of natural numbers. The set of natural numbers is really a nice set to work with. If you're taking number theory or thinking about it, number theory deals with just whole numbers. So you're not just dealing with natural numbers, but for a large part of that class, you will be dealing with natural numbers, whole numbers, because you want to involve zero in those proofs for that class. But nevertheless, so it's really nice to talk about things with the natural numbers, because unlike the real numbers, there's the smallest element, right? Because if you think about, there's no smallest element in the real numbers, but we can definitely clearly see in the natural numbers 1 is the smallest element. I'm thinking about whole numbers. Okay. So the well ordering principle states that every non-empty subset of n has a smallest element. Okay. And that makes sense, right? We can, whatever set, if we have some subset of the natural numbers, if we have some subset of the natural numbers, then we can clearly see the smallest element. And in most cases, because when you're writing sets, you usually write in ascending order. So that first element in that set is usually your smallest element. Okay. So here, the well ordering principle is it's not a proof technique, but it's sort of used sometimes in lieu of the PCI or PMI. And in fact, the PMI, the PCI, and the well ordering principle are equivalent types of proofs, or types of statements, I should say. And there's actually, I think, one of your homework problems, you have to use the well ordering principle to prove the PMI or the PCI. I can't remember which one I gave you guys. So, but it's the reason why I know I had trouble last year in terms of my students not really understanding the well ordering principle, is because the structure is not as straight to the point as the PMI and the PCI and other type of proofs techniques, because it's not really, I don't think we as mathematicians sort of dissociate and say, well, there's a 6th proof technique or a 5th. But it's very useful. And again, if you're a math major, you'll be seeing this principle again. Okay, so just a note, proofs involving the well ordering principle, WOP, generally takes the form of assuming. So the first thing you usually do is assume that a certain property does not hold for the naturals. From that, you can create or produce a non-empty set of natural numbers that don't have that property, and then a contradiction is usually found. So that's generally how it goes. We're going to use the well ordering principle in an example that I'm going to do, but that's sort of the gist of it. Okay, so before we go to the proof using the well ordering principle, I have your third question for the quiz. And it's actually, I forgot to prove it in class. Remember when I introduced mathematical induction, I told you about the smart kindergarten or first year grader who could add 1 up to 100. So this is that proof. So I want you to use the PMI to prove for all n's belonging to the natural 1 plus 2 plus 3 plus ... plus n equals n times n plus 1 over 2. So that's your third problem. Okay, so we're actually going to prove the last proof we proved in the proof we proved in the last video by PCI. Now we're going to prove it using the well ordering principle, because like I said, WOP, PCI, PMI, TMZ. No, okay, I'm sorry. Too many acronyms, sorry. Okay. But we're going to use the well ordering principle, right? Okay. So every natural number greater than 1 has a prime factor. We just proved it using PCI, so now let's look at it using the well ordering principle. Okay. Well, first, we start off our proof just given the information that we know. Let n be a natural number and n be greater than 1. I added a show part in there, so show that n has a prime factor. Well, if n is prime, so you can sort of, when you don't have a structure for a proof, that's why I really like if then proofs, because it's clear to see the structure, and even with induction proofs. Here we don't have a structure, so we can kind of phrase it however we want it. Just make sure we give it, sort of make sure we include all the details, okay? So if n is prime, then n is greater than 1, and n has a prime factor of n, right? Because the smallest prime number is 2, so n is greater than 1, and n has a prime factor of itself, okay? It's its own prime factor, okay? So that's a sort of trivial case, and we're done with that. Now, let's assume n is composite. Then n has factors other than 1 and n, right? Because it's not prime. If it only had factors of 1 and n, it would be prime. But since we're assuming it's composite, then it has factors other than 1 and n. So now we're going to define a set T where whatever that other factor is going to be in this set T. So T equals the set containing m belonging to the naturals such that m divides n, okay, because it's a factor of n, and m does not equal n, and m does not equal 1, right? Because we already said that we're assuming it's composite, so it has factors other than 1 in itself. So there's some other element, and we're calling it m, right? So whenever you have a set, whenever you create a non-empty set, and the reason, again, I want to make sure because this is important, the reason why it's non-empty is because we're assuming n is composite. And so that means it has some factors other than 1 in itself. And so we just created a set T. And ideally what T is a set of the factors of n other than itself and other than 1, because we're assuming it's composite. So by the well ordering principle, and that has to be clear, you don't have to clearly state it, but it has to be clearly shown in your steps that that set is non-empty. Okay, and it's non-empty again because we said n was composite. So therefore we can say by the well ordering principle, T has the smallest element. Let's call it P. And our goal is to show P is prime, because we need to show that n has a prime factor, okay? And we're going to approach this using contradiction. Okay, so let's finish up this proof, and we're going to use contradiction. So let's assume P is composite, all right? Well, that means that P has a divisor D, where D doesn't equal P, D doesn't equal 1, and D is less than P. Okay. All right, so make sure we all agree with that. We're assuming P is composite, and it doesn't equal P and doesn't equal 1 because we're assuming it's something other than 1 and P, because otherwise P will be prime. We're assuming P has another factor other than 1 in itself, okay, because we're assuming it's composite, and of course that D has to be less than P, right? Okay, make sure you understand that. Well, since D divides P and P divides N, because we're calling P that smallest element in our set that divides N, that's not N or 1, then we did a proof that says D divides N, okay? I think we did A divides B and B divides C, then A divides C. I think we did something like that. Well, thus that means D belongs to our set T as well, right? But this is a contradiction. Since D is less than P, and we already stated by the well ordering principle that P is the smallest, I'm sorry, I put an extra element in there, that P is the smallest element of T. Therefore, P is a prime factor of N, okay? So again, this proof, it definitely takes some practice and development using the well ordering principle. So just go back over it and look also in the book as well, which leads me to my last slide. So this is the last slide, and I'm done. So now what I want you to do, because of course I didn't finish everything in that section, but I do want you to go over the other examples in the book in sections 2.5, especially the division algorithm proof. That one is really involved and intuitive. Write it in your notes, and I would say first just write it out on a scrap sheet of paper and see if you understand how how the book went from step A to step B. And then when you've sort of wrapped your head around that, write that in your notes, okay? And the fourth question for your quiz, so there are just 4 questions on the quiz. And the fourth and final question is the fundamental theorem of arithmetic. And this is a theorem that you'll see again as well. So this says every n belonging to the naturals and n greater than 1. This says so basically in the book it says every natural number greater than 1 is prime or can be expressed uniquely as a product of prime. So it's a lot going on in here, and I'm actually, I'm not that tough of a professor, although I am. I just want you to try this, don't leave it blank. Try something. You'll get credit for just trying it, okay? And don't just put the first couple words. I mean, actually think about this proof, try some examples, think about what it says. Don't just look online for it and copy it from a book. You'll get credit just for trying this. I really want you to see if you can try to see and understand this theorem and understand how you would go about setting up a proof. Okay, it's just a really, it's an intuitive proof, so you wouldn't expect something like this on an exam, but the strategy and the way you have to think about it, you would. Those characteristics of strategizing and critical thinking and being analytical and sometimes thinking outside of the box, that's what is really going to take in doing the proofs and even for the exam. So I'm done with the videos. Once you go through this, just start reviewing and really go back over definitions, go over proof structures, and I will see you all next week.